Well, it's an honor to be here for Jeff's birthday. I'm actually Jeff's second student. Lance was the first student, but actually I'm slightly older than Lance, so I'm actually Jeff's oldest student. And so I first met Jeff in 1984 or maybe 85, I can't remember exactly when. And so the graduate students in Jadwin Hall were all up on the fourth floor. And back then, the Princeton Center for Theoretical Science wasn't there, so the fourth floor was kind of a shithole. And the faculty were down on the third floor. And well, okay, going down to see the faculty, well, it was a little scary. But Jeff was only a little scary. He wasn't very scary. So one time I got up the courage to approach Jeff and ask him for a suggestion for a problem. And he had recently written this beautiful paper with Kurt on anomaly inflows. So he suggested a problem on cosmic strings. And I don't remember the problem exactly, but if I remember correctly, there was a situation of having a particle sort of coming near a cosmic string and seeing what happened to the particles that got near the cosmic string. So I went back and up to the fourth floor and started doing some calculations. And actually, I got some very interesting results, and I was kind of excited about it. So a few weeks later, I came back down when Jeff had some free time and talked to him in his office. And I told him what was happening, it seemed to be, was that the particle would come down and would start accelerating along the cosmic string. And I remember Jeff sort of coming up with this big laugh. Okay, I can't reproduce Jeff's laugh, but you all know what it sounds like. There, you heard it. I was hoping he would laugh a little bit. And he said, wow. But I think Jeff knew immediately that I was wrong. But he didn't come right out and say I was wrong. He basically just said, wow, that's really interesting. I wonder where the energy comes from. And I started, and I said, I don't know. And so I went back up to the fourth floor and realized I had made a mistake and nothing very interesting happened. And so, okay, that was the end of that project. But then in the meantime, Princeton was the center of string theory. There was lots of great results happening. And one of the great results was, of course, right after the heterotic string with Jeff and Emil and David and Ryan, there was the orbifolds. And I thought orbifolds were fabulous because you could actually calculate with orbifolds as opposed to back then, the Clavios weren't quite the same thing. So I started working on a project. Okay, and this project took a long time, but Jeff was always very supportive. And one thing I learned about working on orbifolds, of course, is learning everything about E groups, the exceptional groups, and not only that, how to break exceptional groups. And that is always, and everything I learned about that, I learned from Jeff. That has done me a lot of good, I think, in my career. So I'm eternally grateful for all the support he gave me. Okay, so the talk I'm going to give today is 7D supersymmetric Yang mills and supergravity. Well, Pierre was saying that 7 is kind of an interesting number, and so one reason it's interesting for us is that well, we can compute something with it, and so that's sort of what we did. So this work is based on two papers. One, I was sort of thinking I would present when the Jeff Fest was supposed to happen 2 years ago. Okay, and in the meantime, we thought some more about the problem, and we're trying to finish up another project that's related to it. So that sort of worked out okay. Okay, so let me say a little bit about super Yang mills in 7 dimensions. Okay, what do we know about it? Okay, first of all, n equals 1 is maximal, so that means there's 16 supersymmetries. And I should actually say, there seems to be, people who do supergravity would actually call this n equals 2, but other people call it n equals 1, so if there's any confusion, I mean the one with 16 supersymmetries. Okay, and it is not renormalizable. Okay, we know that it has membranes that are basically coming from instantons. It cannot have a UV fixed point. We know this because it's supersymmetric, but these were all classified by Nam, and they're not in 7 dimensions. Its UV completion is almost certainly gravitational. Okay, and it's gravitational. And it has a known holographic dual from right after Maldaceno's breakthrough work. He worked with Itsaki et al. To find a series of holographic duals for maximally Yang mills in various dimensions in flat spaces. And it has certain similarities to 5D pure super Yang mills. And I'll say more about that later. Okay, now we will actually consider a Euclidean version of super Yang mills. And it will, at some point, we'll actually squash this. And we're going to put it on a 7 sphere. The reason we're going to put it on a 7 sphere is we can actually localize it, and we can use holography as well as results from 5D to sort of act as a guidepost for what we want to do. Okay, so in this talk, I'll say something about maximal super Yang mills on S7 and its localization, at least perturbative at first. Then I'll say something about its comparison to supergravity. I'll talk about similarities to N=1 pure super Yang mills and 5D. Non-perturbative contributions. I'll say a few remarks about the other side, and I hope the other side what I mean by that will be clear sooner or later, and then give some concluding remarks. Okay, so super Yang mills on around S7 with radius R. It's completely maximally supersymmetric Lagrangian. We're going to sort of write in this Pastunian way. So the top line here is basically what you get from 10-dimensional super Yang mills from from Brink, Shirk, and Schwartz, but we're going to put it on a sphere, and so that in order to maintain supersymmetry, we have to add extra terms. My notation here is that since it's going to be Euclidean, the components along the spatial directions, I'll use a mu, and then I'll have 3 scalars coming from the dimensional reduction from 10 to 7. And these indices I'll use as capital A's. There'll be some auxiliary fields, these KMs, and there are actually up to 7 of these. And so the F's, okay, these have 10 indices, but these can split into those with the mu indices and the A indices. So F mu A corresponds to a covariant derivative on a phi A, and an FAB is a phi A phi B term like that. Now, so in order to maintain sort of the structure of the 10-dimensional fermions, and since I want my Yang mills to be Euclidean Yang mills, okay, it means I have to keep a time-like direction. And so what the trick you sort of do is you sort of assume that one of the scalar fields is along a time-like direction. Okay, and that means that this phi naught component will have the wrong sign kinetic term. Okay. And in 7D, if you can do an ordinary dimensional reduction of 7D Yang mills, you end up with an SO3 R symmetry. Because we have this wrong sign here, it actually is an SO1, 2 R symmetry. And except for 4 dimensions, 7 dimensions is the only other dimension where when you put it on the sphere, you actually don't break the R symmetry. So in other cases, you break it down to a subgroup of whatever the R symmetry should be. Okay, so then when you localize, just a quick review about what localization will mean is, so when you localize a theory, you have to choose a killing spinner. And from this killing spinner epsilon, you can construct a killing vector. And this killing vector runs over all 10 dimensions. And so just from the properties of gamma matrices in 10 dimensions, you can argue that this killing vector is null. Okay, so we can choose one component to be, say, along the 0 direction, so it has 1, and we'll choose the part along the other directions, the other scalar directions to be 0. And so that means that the killing vector along the 7 sphere squares to 1. And the localization locus, so basically when you localize a theory, it collapses to a subset of all possible field configurations. And so what it does is that it's almost collapses to 0, but not quite. okay, it splits into the gauge fields, the gauge field strengths split into a vertical part and a horizontal part. And the vertical part, okay, is basically, it runs along the V mu direction here. So we write this using this contact one form, where I use the contraction along V of this contact one form. And the horizontal part splits into three parts. So basically it's an F plus, so it's sort of the self-dual part, the anti-self-dual part, and a part that's proportional to the Kähler form on the 6D space that this one form, that this vector field is fibered over. Okay, so when you localize, then you find out that the vertical part is 0, okay, and the scalar phi naught, okay, is constant, and the auxiliary parts are related to this field phi naught in this way, and then there's a three form that I call this capital phi, which is made up out of the other two scalar fields, the 8 and the 9, okay, and that part, its curvature part is also has no components along the vertical direction, and then there's a relation between this three form and this F plus, and finally this relation between the part here like that. So most of this I won't need to worry about, but I'm just putting it there for completeness. Okay, so first we want to consider the sort of the perturbative regime. So in the perturbative regime, basically we can set the field strengths equal to 0 and this three form equal to 0. And so basically all we're left with is this field phi naught. Everything else is basically set to 0, and this field phi naught is constant on the sphere. Okay, so basically it just, the partition function just reduces down to these constant modes, and it basically becomes a matrix model, or a form of a matrix model. In the 7D case, you can actually compute this and you get something that looks like this. So this part here, this is the part coming from the Yang-Mills action, and this part is basically coming from when you localize, there's a Gaussian contribution around the localization locus, and you get this contribution here. And so G naught squared is a bare coupling, so it's just the term that appears in the Lagrangian. And actually this term here actually is divergent, okay? And not as it's divergent, the divergence depends on the phi. Okay, so it's not just a constant term that I can just drop. There's actually some phi, this phi dependence here. And by the way, I'm writing this in terms of sigma, which is a dimensionally, it's a dimensionless variable phi, sigma. Okay, so I need to write.
Where does the power n squared plus 1 come from? N squared to the power n squared plus 1, where does that come from?
It's basically counting all these other modes. So it's
some symmetry, is that representation of some?
Yeah, you can do these Todd classes and get to counting like that. So anyways, you need to regularize it, and so the way you can regularize it, you can multiply and divide by this factor e to the minus sigma I squared. In which case, this term is still divergent, but it's only divergent up to a constant, so you can divide out the constant. And then you have this term here, okay, and you see that this term is just a product term. You can write this product as a product of this times a product of that. And because the sums of the sigma, because we're talking about SUN, the sums of the sigmas are 0, you can rewrite this term basically in terms of a sum over the eigenvalue squared. And so anyways, when you do that, you end up with something now that is finite over here, and you actually end up shifting what you mean by the coupling. And the coupling, this 1 over G Yang-Mills squared, is the bare part with some cutoff term here. And the cutoff is basically you're counting over the modes. Okay, so you can think of this as basically being you have some UV cutoff, lambda, and r being the radius of the sphere, okay, gives you basically this maximum part that you cut off by. Now, in order for this partition function to be well defined, we should assume that G naught squared is greater than 0, Okay, but this doesn't actually mean that G angle squared has to be greater than 0. It could actually be less than 0. And this, we'll see, will still be sort of well-defined. Okay, so when you solve a matrix model, okay, often what you do is you solve by the saddle point, by solving by the saddle point. So you find where the extrema are of the saddle point, and what you end up with is a very simple equation, basically. So this part here is basically coming from the action. This part here is coming from the modes that we had before, and actually it's a very simple term. It's just 2 pi times this 1 minus sigma squared times the hyperbolic cotangent of the difference between the eigenvalues like this. And lambda is this dimensionless Latouf parameter here. Okay, so to get some idea of what should happen, you can think of this term here is giving you a central force that acts on your eigenvalues. And this term here, okay, is giving you a force between eigenvalues. And you can see then that when lambda is much, much greater than 1, okay, the force is towards the center is very high. But for the eigenvalues, it's actually repulsive when they're close together. That's what this is telling you. Okay, and so basically for very small values of lambda, you're basically very close to a Gaussian matrix model. Okay, and so you're going to find that you're going to get a Wigner distribution. Okay, so the first thing you might try to do is you want to set lambda to be infinite. Okay, so you go to the infinite coupling limit. So basically then you end up with basically a straight line going up like this. But because of the way that this self-interaction terms works, it's repulsive at short distances, but it actually becomes attractive at large distances. Okay, so actually when you go to lambda equals infinity, you get a distribution of eigenvalues that looks like this. So there's like 2 humps, okay, that are basically separated by order 1. Okay, so the nearby eigenvalues are sort of repulsed from each other, but the eigenvalues over here are sort of putting an attraction to the eigenvalues over here and prevents them from spreading out to infinity. Okay, but in this case, since this is of 1 and 1, okay, the eigenvalues are actually not widely separated. And our experience is that in order to compare localization results to results in supergravity, you need sort of a wide separation between eigenvalues. So what you can do then is that you can actually then consider the case where we actually take lambda to be less than 0, okay, in which case it slopes up like this. So now the eigenvalues are being pushed away from the center, okay, and they're pushed away, but on the other hand, you also have this force such that they're actually attracted back. Okay, so actually what happens is this lump that I had over here, these 2 lumps here, oops, these 2 lumps here, I keep hitting the wrong button. These 2 lumps here, okay, just start spreading out, okay, and you end up with these 2 lump solution like this, and these can spread very far apart. And so you basically have these two terms here that looks like spikes in your distribution. Okay, and so you can, it's simple to compute the separation between these spikes. Okay, and it turns out that this separation is just given by basically twice this number here. Not only that, this result is actually finite this result is actually valid for finite n. Normally, to do a saddle point, you need n to be large. But since the separation is still, I could have just 1 eigenvalue over here and 1 eigenvalue over here. Okay, and so actually, it's actually sharply peaked in this case. Okay, so you can do something like that. Yep.
This potential had a very simple form, just some hyperbolic cotangent or something.
Yeah.
The one before.
Yeah.
But your original sort of determinant and so on was extremely complicated. I thought the simplification was happening because of large n.
No, it's not because of large n. It's actually this is not a large n result. Okay, it's just the result of it's just if you solve the saddle point equation. And so if you looked at it, so basically what it is if you took the log of that determinant, okay, and took a derivative with it, it simplifies a lot. Okay, and so basically that's what happens. Okay, because the actual term, if you take the log, you have Li3 function, polylogs of threes and things like that. But the determinant turns out to be easy. I mean, the derivative of it turns out to be very simple. Okay, so you can actually then plug this back in, this result back for your distribution back into the partition function, and you find that the free energy then is just given by this result here, 16 pi to the 10th n squared divided by 3 lambda cubed. Okay, and you can also, the other thing you can do is that when you localize, you can look at supersymmetric observables, and there is an interesting supersymmetric observable, namely a Wilson loop that goes around the equator, or I should say a Maldacena Wilson loop. It goes along the equator. And so that, in this case, when you localize, the only contribution is coming from the scalar part. Okay, and you know the eigenvalue distribution. Okay, it's basically more or less this. Okay, and you see then that the expectation value for this Wilson loop is this exponent here. So actually, remember, lambda is negative, so actually this argument is actually positive. Okay, and if lambda is small but negative, okay, the eigenvalues are farly separated. Okay, and so this, you get a result that looks like that. What time did I start? I forgot to look at the time.
Forgot, sorry.
Three? Because I
Yeah,
think Greg went.
You're like
Yeah.
20 minutes in.
Three.
You're 20
20
minutes.
minutes in, okay.
Yeah.
Okay. So then, okay, so now that we have the result, we can actually compare it to supergravity. And so this particular supergravity, we're actually gonna, to borrow Pierre's phrase, we're gonna go down a rabbit hole a little bit on this. So the way you should think about the supergravity is we're thinking about a Euclidean gauge theory on a sphere. Okay, so what we're actually looking for are Euclidean branes that wrap around an S7. Okay. So there's a whole bunch of work done by Hull in the late 90s about thinking about what he was thinking about, how he should, what it means to have Euclidean D-branes. So he called these E-branes. And so what you have to do is you have to T-dualize, what he did is he T-dualized along the time direction in 2B. Okay, so that brought him to something he called the 2A star theory. So a normal D-brane always has a leg along the time direction, but by T-dualizing the time direction, you get rid of that leg along there and you end up with something Euclidean. Okay, now this still has a 1,9 signature, and all the DP branes in 2B then become EP branes in 2A star. Okay, now the EP branes have imaginary tensions, and you can sort of understand this pretty simply because, say, if you think about an E1 brane, it just has a leg along one space-like direction. You can think of it as a space-like world line. So it's a world line for a tachyon. So it has a tachyonic mass. Okay, so it has an imaginary mass. Okay. So the mass squared is negative, so the mass is imaginary. Now, the EP branes are actually BPS, and since they have imaginary masses, or imaginary tensions, if we're talking about higher dimensional objects, then they have to have imaginary charges. Okay, and that means they source imaginary fluxes. So then, okay, I told you we're going down a rabbit hole. Then we can consider the M theory uplift of this theory. In the strong coupling limit of 2A star, E1 branes are Kaluza-Klein modes on the M theory circle. Okay, but they're tachyonic, so that means this M theory circle has to be time-like. So the final thing is a 2,9 signature. I was afraid you were going to ask me a question, yes?
What does it mean to take the strong coupling limit of a theory which has a tachyon? It barely makes sense as a classical theory.
Well, I'm not.
You consider fluctuations in this unstable theory, and not only that, to send the coupling to infinity.
Well, I'm not actually doing it. Okay, I'm just talking about the supergravity side theory right now. Okay, so on the gauge theory side, I mean,
Well, but to the strong coupling.
I'm actually doing more than strong coupling. I'm going through strong coupling and going it down to the other side.
The S matrix might be defined by analytic continuation.
Yeah, you can define it, yeah.
So there's a tachyon?
Where's the tachyon?
This is a tachyonic theory.
No, it's, you mean, no, I mean, everyone in the amplitudes world really works in 2-2 signature.
Yeah.
And they define it by analytic continuation.
So I'm gonna analyze it.
It's not the same as a tachyon in string theory, it's,
No,
negative.
it's sort of a, I'm
But it
gonna
has
handle.
tachyonic mass.
Yeah, well, my,
Okay,
Yeah,
go
I don't
on.
know that it does make sense, but it's not obvious it doesn't.
okay, I'll take that as thumbs up. Okay, so anyways, then, so so Bowman and Goddison actually doing this, they actually found the supergravity tool for the case on S7, and it turns out they did it for various dimensions, and it turns out the S7 was actually more or less the simplest case, aside from the 4D case. In this case, symmetric has this form, so you have the 7 sphere metric, and you have this part here. So this part is basically a this is sort of like the rotation of S2, okay, but this preserves an SO1 comma 2. This has an SO1 comma 2 isometry. Then I have a sort of a holographic direction, if you will, a rho, and I have then various relations between the dilettante field and all these different other terms in here. Okay, and there's an F2 that's going through this d omega 2, going through this 2-dimensional surface here, and it's imaginary. It has an imaginary component. Okay, so and also it turns on this H3 field as well. Now the question is, should we be using the bare or the renormalized G angle squared? Okay, and I would say we should use the renormalized case. And now, but remember, we're assuming that G angle squared is less than 0. Okay, and since G angle squared is proportional to GS, it looks like GS is going to be negative. And if GS is negative, it means e to the 2 phi here is going to be negative. So the only thing you can sort of do to get a sensible metric is sort of analytically continue this rho variable, which is supposed to be positive in the positive direction to the negative direction. In doing that, also this flux remains the same, but this H3 changes sign. Okay. So basically what we've done is we sort of flip the dictionary around and we get something like this. So as we take rho to infinity, 2 phi goes to infinity, we should consider this m star uplift. Okay, and here now the solution lies on an H2 comma 2 mod Zn. Okay, so this is some hyperbolic space with 2 time-like directions. We're modding out by Zn times an S7. Okay, so it has a very simple solution just with this very weird signature. The metric is very simple. It just has this form here where this DS4 it looks basically like well, it's sort of like a rotation of the S3 modded out by a Zn symmetry here. So this actually has an AN minus 1 singularity, but you get an expression like this. And then the four-form field strength, okay, is imaginary, and it's going in through this H22. Okay, and omega is basically the angle along this time-like circle, and you can see that it has there's an overall minus sign, so it has the wrong side term here. All right, so then we can look at this dictionary between the 11-dimensional Planck length and G angle squared. Okay, now this is positive because we made this term negative, and so we have the minus sign here, and we get that. Okay, so now you want to compare results. Okay, so we have a solution, and so we know. So then, what's the normal thing that you do? Okay, so to look for a BPS Wilson loop on the S7 equator, what we should do is we should take an M2 brane in this theory, and it should have legs along the S7 equator and along the time-like M theory circle and along sort of the holographic direction rho, and both of these all lie on H22 mod Zn. Okay, and you can plug that in, you can compute this action, and you find that the tension then is given by this expression here, and then you use the dictionary and you find out that it actually matches, okay, what you had for the BPS Wilson loop from the gauge theory localization. So then you can also do the free energy. You can plug that in. Okay, you do the rules. Okay, you need to do a wick rotation, okay, when you do this, but you're only wick rotating one direction, you're not wick rotating two directions. Okay, let me not get into that. But you do that, okay, and you get the right result for the free energy, okay? And you can see that the supergravity is trustable in the sense that the radius of r cubed is much greater, that the radius r is much greater than L11, basically tells you that 1 over a g angle squared has to be much greater than 1, okay? And this can even be true when n is finite, okay? The matching continues to hold. So I said before that you can trust you can trust the you can trust the saddle point even for finite n in this limit, and you can see then that finite n is fine in the supergravity as well. And this was actually observed also even by Itaki et al. In 1998, that actually they can apply this M, they weren't doing M star theory, but they had M theory, okay, and that the results should still work for finite n. That the result is still trustable for finite n. In the case where you're in the M theory regime. Okay, so let me just say a few things about similarities to 5D. Okay, so in 5D, we can consider, we put this, this should be n equals 1 on a round S5. And in this case, the eigenvalue equation to the limit of large, okay, forget the hypermultiplet mass. I've basically taken the hypermultiplet mass to infinity, and so that's going to act as a cutoff. And you get an equation that's basically very similar to what you had in the 5D case. The only difference is that this power on this pi, and in the 7D case, there was no 1/2 here. But otherwise, it's qualitatively exactly the same. Okay, so at strong coupling, you get a eigenvalue distribution with these two humps. You can go pass through to the other side, where you go to small negative coupling, okay, and you get these two lumps separating from each other. And basically, you can think of it as your Coulomb branch starting with an SUN is broken down to an SUN divided by 2 times an SUN divided by 2 times a U1. And actually, when you do this, you find you generate an effective coupling for this U1, which is equal basically to -1 over lambda, which is greater than 0. So it all seems to make sense. And the U1 is enhanced actually to an SU2. Okay, now this we understand very well, okay? So one way to understand this theory is to think about it in flat space and think about building PQ webs for this theory. So if I consider, say, just the SU2 case, okay, a PQ web, I would have two D5 branes running
Sorry,
along.
I have this cousin of the, when you say write negative coupling, I assume you mean negative coupling squared.
Yeah, okay, I mean negative coupling squared,
Well,
okay.
but then, does it really make sense
Well, I think you showed that it makes sense.
for negative?
It means you
It
go to
means
the
something
UV,
else.
Yeah,
it means you go to the UV and turn on the opposite sign relevant.
Yeah, so you
definition.
go to your fixed point, you have an SU2 global symmetry,
Yeah.
and that SU2 global
But then it's-
symmetry changes.
Okay, but you shouldn't think of it as the negative sign of the other one.
I agree, but it's a well-defined theory on the other side. I'm just saying from the matrix model point of view.
I'm very impressed that doing the calculation, just analytically continuing G squared through the strong coupling point.
Yeah.
You land on your feet.
Well, no, it's okay. I think it's not as great a feat as that, I don't think. So, but the reason why, but from PQ brain web, the way you can sort of understand it is that, so you have two D5 brains running this way, you have two NS5 brains running this way, and to keep preserved attentions, you have these 1-1 brains coming out of here. And this has a Coulomb branch, and so you can pull the D5 brains away from each other, and at the same time, the NS5 brains move away from each other. And so the W bosons in this case are strings that run between the D brains, but there's also instanton particles, which are D strings that run between the NS5 brains. And you can see basically that the mass for these instanton particles, which I call MI, are basically the Coulomb branch parameter phi plus 4 pi over G angle squared. And 4 pi over G angle squared is the minimum distance between the NS5 brains when phi goes to 0. So basically pulling this rectangle down to just inside there. Okay, so if I then go down to where this thing shrink, if I then increase G angle squared, basically this rectangle shrinks down like this, and then it comes to 0, and I hit the Seiberg dual point. Okay, and then I can quote unquote go through the Seiberg dual point, and it's basically pulling these guys up like this. Okay, and in which case then sort of in the SU2 case, the W bosons sort of switch roles with the instantons. Okay, so the instantons would be massless at the base of the Coulomb branch, and the W particles, okay, their minimum mass, okay, is 4 pi squared over G angle squared, and then it's 5 pi. Okay, now, how do you see this doing localization? Yep, 5 minutes? Okay. How do I see this doing localization? So, well, so when I localize on this theory, okay, what you actually need to do is you need to squash it. And the reason for that is in order to get this thing to be well controlled. Okay, when I squash it, basically my killing vector will be a components along these three angular directions that I have. So I'm writing the S5 matrix in terms of these coordinates Z1, Z2, and Z3, okay, such that their squares are set to 1. So the localization locus in this case is that basically the star of F along this vector is equal to minus F, and phi is equal to 0. Okay, now this orbit actually generated by V actually doesn't close for generic Z1, Z2, and Z3. Okay, and omega I. Okay, where omega i's are these squashing parameters here. So that means if I run this orbit of V around, it's basically going to end up being dense on a 3 torus over Z1, Z2, and Z3. And it actually suggests for these orbits that you have to actually set F equal to 0, IVF equal to 0. Sorry, the IVF equals 0, which actually is a consequence of this equation, implies that F equals 0 in order to avoid singular configurations. And so that means that the only non-trivial contributions you can get are only on these fixed circles, Z1, Z2, Z3 equals either 1, 0, 0, 0, 1, 0, or 0, 0, 1. Okay, and so these will be closed orbits. And these will correspond to point-like instantons along S1. So the space transverse to each of these closed orbits can be replaced with a C2, and the C2 is twisted, okay? And so when you twist this thing, you end up then with non-perturbative contributions from each fixed circle to the partition function in 5D, and this turns out to be the Nekrasov partition function. So you get this Nekrasov partition function, and well, okay, let me, you can write it in these terms. Okay, you have this single sine function, okay, which is a fancy way of saying a sine function, which depends on these equivariant parameters of the various omegas here. And for small negative G angle squared, okay, which is what we're sort of interested in, when I just have the SU2 case, these two eigenvalues are forced far apart from each other. And in this case, so I define some delta sigma, which is equal to sigma 1, 2 plus this, so this term could be small. Okay, you find that this instanton partition function actually simplifies greatly. And basically what you get is a sum over all the various sort of instantons multiplied by this function over here. Forget what this function is. Okay, but the main thing to see is that you end up with this instanton mass, okay, that basically behaves as 5 prime. Okay. So going into this negative region, you can see then that these instantons actually work like this. And basically this is guaranteed to work by some arguments of, by the original construction of Lockhart and Barfoot. Okay, so now let me do the same in 7D. Okay, so for generic squashings, the orbits of E do not close, but are dense on the T4. Okay, and as in 5D, this suggests that we should restrict to some non-perturbative configurations, okay, that are closed orbits over the fixed points on some 6-dimensional base. Okay, but this turns out to be too strict. So instead, you should actually suppose that the orbits are restricted to lie in fixed squashed 3 spheres. That is, they're subspaces of this S7, okay, such that they satisfy these sort of conditions like this, where so I not equal to j, j equals 1 up to 4. Okay, and you can see that there's 6 possible choices for it, given by the 6 possible choices for I and j. So anyways, our conjecture is that any forms in the localization locus that has components on the squashed S3 are going to be forced to be 0. Okay, so that means that this 3 form is going to be 0, and this part of the field strength that has along the Kähler form is going to be 0. And so basically this then means that F plus also has to be 0. So the only thing that's going to be left are going to be these instanton membranes that are basically wrapping the S2 that are hop fibered basically, which are the hop fibered base over an S3. Okay, so when you do that, so what happens is that, okay, so you find out you do what Microsoft did, borrowing on what Losov and Greg and all these other people did. You look at the ADHM variables for these fields. So your ADHM variables are going to be fields on this squashed S3. Okay, and when you have field theory on S3, what shows up is not single signs, but double signs. So you actually, it involves a bunch of double sign functions, and you get an expression like this. And you can, looks like you have this term over here, and this is the part coming with the membranes. So at first it looks like this is going to be highly divergent, because remember, I want to take G angle squared to be negative, okay, and small, so this would be a very large term. However, it turns out that this part inside here is actually going to save you, okay, and basically what's going to happen is that you do some manipulations, and you end up with some membrane tensions, okay, that actually go like this, multiplied by the SV volume. I should also say that in this instanton, the Z instanton in this case, okay, has 4th order poles, and the poles are basically because when you set the omegas to be equal to each other, you enlarge, the space where you have closed orbits, okay, and so it ends up being divergent. But these 4th order poles will actually cancel, okay, when you add up all the contributions of all these 2 to 3 spheres. Okay, so I'm about out of time. So anyways, let me just end here. Okay, I'll skip this part. So anyways, we have argued that the proper regime to compare super Yang-Mills 7D is for weak negative coupling. And we have contributions to the localized partition function, including those from massless instanton branes. We have said, okay, well, I didn't actually get to this part, but let me suggest it now. So we might ask, what's the equivalent, what's the theory on the other side? What does it correspond to having a negative G angle squared? So what we believe is that it's 7D supergravity. So it's not a leap of faith. But in order to show that, what we would hope is that we can sort of localize supergravity in 7D. And there's been some beautiful work done by Atish and Samir, and also Atish and Nadav Tucker and Gomez in this part here, about localizing supergravity theories. In particular, this case here, they considered ADS4 cross S7 mod ZK. So the dual for ABJM theory, and they looked at a consistent truncation for that theory, which is ADS4, and they localized that, and they were able to match the gauge theory side and on the field theory side. And not only match at the leading order, but match it, in fact, the orders of 1/n. So we hope that something similar can work here. Okay, so finally, I've run out of time, so I just wish to say happy birthday, Jeff, and thanks for being a great advisor.
Joe, questions?
So it's very naive. In the 5D case, which I think I understand, you go through a transition, and at the transition point, there's a non-trivial fixed point.
That's right.
Non-trivial fixed point. What happens at the transition point in 7 dimensions?
It seems like nothing happens, because it's not it can't be a fixed point,
But it could be some point of strongly coupled.
but certainly some strongly coupled theory.
But it's not nothing. Something special happens at that point. It's not a smooth transition.
Well, that's quite possible. It's not smooth. I'm not sure. I don't know, to be honest.
It will be a strong coupling limit of string theory.
Yeah.
I don't think it's something that we've seen before. So it could be something really interesting.
No, I agree, and we've been struggling for this for a long time, and so for a couple of years now. So our main thing is about finding the instantons and finding that. Okay, what you have is, it seems like you have, on the other side, you have these branes with basically that can have zero tension. Okay, so I was originally hoping it was going to be little M theory, or something like that, but I don't know what it is. So the only thing that we have is we have some evidence that, this supergravity seems, we can compare these two things, and that this seems to be the regime where we make the comparison. But to make the comparison, it's not at the fixed point. You have to go through. I don't know.
But it's surprising that it matches. It didn't have to match.
Well, yes and no. I mean, there is sort of a supergravity, construction from branes. The usual story of building up. It's surprising that I had to go to negative coupling to actually do it. But I think the reason why I had to go to negative coupling is because in lower dimensions, starting from 5 down, if you're in maximally supersymmetric, okay, the coupling doesn't run. Okay, but once you get to 6, it starts running. And that has a lot to do with it. Okay, in fact, the running of the coupling is why I had the divergence. So basically, I had to normalize my coupling. So it has something to do with that.
And you mentioned before it's non-renormalizable, but I never saw any of the higher dimension operators that come.
Yeah, well, so
You're not looking at non-supersymmetric enough sources to see them, or what?
Well, so when I localize, I have to look at supersymmetric observables. And so the assumption, which I believe has never been proved, is basically any other term, all these non-renormalizable terms you ever generate are Q exact. Okay, and they don't actually contribute then to the localization, to the partition function. So, but I believe it's never been proved, yes.
And
But did you say something about it means gravity to complete it?
I believe, yeah, I mean, because you can't decouple D6 branes from the bulk, basically. So,
I see.
I mean, that's the argument.
The holographic bulk supergravity is it's a singular geometry.
Well, it is singular because it has this AN -1 singularity on it. So I don't know what to do with that, but just around it, the curvature is small. So I mean, it could be that ruins everything, but hopefully not.
okay, no further questions. Let's thank you again. We're running a little late, so let's gather at 4:20 as per schedule.